Pyrite.
The mineral pyrite, or iron pyrite, also known as fool's gold, is an iron sulfide with a formula Fe(S)2. This mineral's metallic luster and pale brass yellow hue give it a superficial resemblance to gold, hence the well-known nickname of fool's gold. The color has also led to the nicknames brass, brazzle, and brazzle, primarily used to refer to pyrite found in coal. Pyrite is the most common of the sulfide minerals. The name pyrite is derived from the Greek purites, pyrites, of fire, or in turn from fire. In ancient Roman times, this name was applied to several types of stone that would create sparks when struck against steel. Pliny the Elder described one of them as being brassy, almost certainly a reference to what we now call pyrite. By Georgius Agricola's time, the term had become a generic term for all of the sulfide minerals. Pyrite is usually found associated with other sulfides or oxides in quartz veins, sedimentary rock, and metamorphic rock, as well as in coal beds and as a replacement mineral in fossils. Despite being nicknamed fool's gold, pyrite is sometimes found in association with small quantities of gold. Gold and arsenic occur as a coupled substitution in the pyrite structure. In the Carlin-type gold deposits, Arsenian pyrite contains up to 0.37 Wt% gold.
Uses.
Pyrite enjoyed brief popularity in the 16th and 17th centuries as a source of ignition in early firearms, most notably the wheellock, where the cock held a lump of pyrite against a circular file to strike the sparks needed to fire the gun. Pyrite has been used since classical times to manufacture copperas, that is, iron, sulfate. Iron pyrite was heaped up and allowed to weather. An example of an early form of heap leaching. The acidic runoff from the heap was then boiled with iron to produce iron sulfate. In the 15th century, such leaching began to replace the burning of sulfur as a source of sulfuric acid. By the 19th century, it had become the dominant method. Pyrite remains in commercial use for the production of sulfur dioxide, for use in such applications as the paper industry, and in the manufacture of sulfuric acid. Thermal decomposition of pyrite into Fe(S), iron, sulfide, and elemental sulfur starts at 550 DEGC. At around 700 DEGC PS2 is about 1 atmospheres. A newer commercial use for pyrite is as the cathode material in Energizer non-rechargeable lithium batteries. Pyrite is a semiconductor material with a band gap of 0.95 eV. During the early years of the 20th century, pyrite was used as a mineral detector in radio receivers, and is still used by crystal radio hobbyists. Until the vacuum tube matured, the crystal detector was the most sensitive and dependable detector available, with considerable variation between mineral types and even individual samples within a particular type of mineral. Pyrite detectors occupied a midway point between galena detectors and the more mechanically complicated pericon mineral pairs. Pyrite detectors can be as sensitive as a modern 1N34A diode detector. Pyrite has been proposed as an abundant, inexpensive material in low-cost photovoltaic solar panels. Synthetic iron sulfide is used with copper sulfide to create the experimental photovoltaic material. Pyrite is used to make marquisite jewelry. Marquisite jewelry, made from small faceted pieces of pyrite, often set in silver, was popular in the Victorian era. Marquisite jewelry does not contain marquisite, which is a medieval term that encompassed both pyrite and the mineral now called marquisite.
Formal oxidation states for pyrite, marcasite, and arsenopyrite.
From the perspective of classical inorganic chemistry, which assigns formal oxidation states to each atom, pyrite is probably best described as Fe2 plus S22. This formalism recognizes that the sulfur atoms in pyrite occur in pairs with clear SS bonds. These persulfide units can be viewed as derived from hydrogen disulfide, H2S2. Thus pyrite would be more descriptively called iron persulfide, not iron disulfide. In contrast, molybdenite, MoS2, features isolated sulfide, S2. centers because the oxidation state of molybdenum is Mo4+. The mineral arsenopyrite has the formula Fe is S. Whereas pyrite has S2 subunits, arsenopyrite has As units, formerly derived from deprotonation of H2 As. Analysis of classical oxidation states would recommend the description of arsenopyrite as Fe3+, As 3.
Crystallography.
Iron pyrite Fe2 represents the prototype compound of the crystallographic pyrite structure. The structure is simple cubic and was among the first crystal structures solved by X-ray diffraction. It belongs to the crystallographic space group Pa3 and is denoted by the structure-Pyrite notation C2. Under thermodynamic standard conditions, the lattice constant of stoichiometric iron pyrite Fe2 amounts to 541.87 pm. The unit cell is composed of a Fe-face-centered cubic sublattice into which the S ions are embedded. The pyrite structure is also used by other compounds Mx2 of transition metals M and chalcogens X equals O, S, CNTe. Also certain dipnictides with X standing for P, As and Sb etc. are known to adopt the pyrite structure. In the first bonding sphere, the Fe atoms are surrounded by 6 S nearest neighbors, in a distorted octahedral arrangement. The material is a diamagnetic semiconductor and the Fe ions should be considered to be in a low-spin divalent state, as shown by most Bauer spectroscopy as well as XPS, rather than a tetravalent state as the stoichiometry would suggest. The positions of X ions in the pyrite structure may be derived from the fluorite structure, starting from a hypothetical Fe2+, S2 structure. Whereas F ions in Ca-F2 occupy the center positions of the 8 subcubes of the cubic unit cell, 1/4 1/4 1/4, etc., the S ions in Fe2 are shifted from these high symmetry positions along less than 111 greater than axis to reside on, here, and symmetry equivalent positions. Here, the parameter U should be regarded as a free atomic parameter that takes different values in different pyrite structure compounds. Iron pyrite Fe2, U, S, equals 0.385. The shift from fluorite U equals 0.25 to pyrite U equals 0.385 is rather large and creates a SS distance that is clearly a binding one. This is not surprising as in contrast to F, an ion S is not a closed shell species. It is isoelectronic with a chlorine atom, also undergoing pairing to form Cl2 molecules. Both low-spin Fe2+ and the disulfide S22 moieties are closed-shell entities, explaining the diamagnetic N semiconducting properties. The S atoms have bonds with 3 Fe and 1 other S atom. The side symmetry at Fe and S positions is accounted for by point symmetry groups C3I and C3, respectively. The missing center of inversion at S lattice sites has important consequences for the crystallographic and physical properties of iron pyrite. These consequences derive from the crystal electric field active at the sulfur lattice site, which causes a polarization of S ions in the pyrite lattice. The polarization can be calculated on the basis of higher-order Madelung constants and has to be included in the calculation of the lattice energy by using a generalized Born-Haber cycle. This reflects the fact that the covalent bond in the sulfur pair is ill accounted for in the strictly ionic treatment of Madelung theory. Arsenopyrite has a related structure with heteroatomic S pairs rather than homoatomic ones. Marcasite also possesses homoatomic anion pairs, but the arrangement of the metal and diatomic anions is different than in a pyrite. Despite its name, a chalcopyrite does not contain dianion pairs, but single S2 sulfide anions.
Crystal habit.
Pyrite usually forms cuboid crystals, sometimes forming in close association to form raspberry-like rhomboids. However, under certain circumstances, it can form anastomosing filaments or T-shaped crystals. Pyrite can also form dodecahedral crystals, and this suggests an explanation for the artificial geometrical models found in Europe as early as the 5th century BC.
Varieties.
Cateorite, Cos2, and Vasite, Anis2, are similar in their structure and belong also to the pyrite group. Bravowite is a nickel-cobalt-bearing variety of pyrite, with greater than 50% substitution of Ni2+ for Fe2+ within pyrite. Bravoite is not a formally recognized mineral, and is named after Peruvian scientist José J. Bravo, 1874–1928.
Distinguishing similar minerals.
It is distinguishable from native gold by its hardness, brittleness and crystal form. Natural gold tends to be anhedral, irregularly shaped, whereas pyrite comes as either cubes or multifaceted crystals. Chalcopyrite is brighter yellow with a greenish hue when wet and is softer, 3.5-4 on Mohs scale. Arsenopyrite is silver white and does not become more yellow when wet.
Hazards.
Iron pyrite is unstable in the natural environment. In nature it is always being created or being destroyed. Iron pyrite exposed to air and water decomposes into iron oxides and sulfate. This process is hastened by the action of acid Ethiobacillus bacteria which oxidize the pyrite to produce ferrous iron and sulfate. These reactions occur more rapidly when the pyrite is in fine crystals and dust, which is the form it takes in most mining operations.
Acid drainage.
Sulfate released from decomposing pyrite combines with water, producing sulfuric acid, leading to acid rock drainage and potentially acid rain.
Dust explosions.
Pyrite oxidation is sufficiently exothermic that underground coal mines and high-sulfur coal seams have occasionally had serious problems with spontaneous combustion in the mined-out areas of the mine. The solution is to hermetically seal the mined-out areas to exclude oxygen. In modern coal mines, limestone dust is sprayed onto the exposed coal surfaces to reduce the hazard of dust explosions. This has the secondary benefit of neutralizing the acid released by pyrite oxidation and therefore slowing the oxidation cycle described above, thus reducing the likelihood of spontaneous combustion. In the long term, however, oxidation continues, and the hydrated sulfates formed may exert crystallization pressure that can expand cracks in the rock and lead eventually to roof fall.
Weakened building materials.
Building stone containing pyrite tends to stain brown as the pyrite oxidizes. This problem appears to be significantly worse if any marquisite is present. The presence of pyrite in the aggregate used to make concrete can lead to severe deterioration as the pyrite oxidizes. In early 2009, problems with Chinese drywall imported into the United States after Hurricane Katrina were attributed to oxidation of pyrite. In the United States, in Canada, and more recently in Ireland, where it was used as underfloor infill, pyrite contamination has caused major structural damage. Modern tests for aggregate materials certify such materials as free of pyrite.
Pyritized fossils.
Pyrite and marquisite commonly occur as replacement pseudomorphs after fossils in black shale and other sedimentary rocks formed under reducing environmental conditions. However, pyrite dollars or pyrite suns which have an appearance similar to sand dollars are pseudo-fossils and lack the pentagonal symmetry of the animal.